So for this section, Unit 4B, we're going to talk about interest and the power of compounding versus continuously compounding versus simple interest, okay? So a few definitions, a few things we need to know. The principal is in financial formulas is the balance upon which interest is paid. Now this can be, remember, this can be for money invested or borrowed. Okay, so when they talk about principal, it's either the principal meaning how much you borrowed or how much you invested. So just keep that in mind. It could be, good or bad depending on if you're investing or borrowing. Simple interest is interest paid only on the original principal and not on any interest added on later dates. Compound interest is interest paid both on the original principal and on all interest that has been added to the original investment. So this is kind of the more basic one, simple interest, and then this is a little bit more interesting of a problem. Okay. So I'll first kind of talk to you guys about simple interest, and then we'll go from there. So it says, while banks almost always pay compound interest, bonds usually pay simple interest. Okay, so suppose you invest $1,000 in a savings bond that pays simple interest of 10% per year, which again is very unlikely you'd actually ever get this. That's a really high rate. How much total, but this is just for an example, how much total interest will you receive in 5 years? Let's see here. If the bond paid compound interest, would you receive more or less in total interest? So let's see. So here's the formula for simple interest. Now, you should have seen this formula before at some point in your life. And the formula says interest equals principal times rate times time. Okay. And when you're talking about time in terms of simple interest, we're always talking in terms of years. Okay. So T will always be T will always be in terms of years. So if they say 5 years, you put a 5. Now, what if they say for a half a year? Then you would put 6 out of 12 or 1/2 because you have to do it in terms of years. So if they said, 6 months, 6 months would only be half a year. Okay. So in this problem, it says, how much total interest will we receive in 5 years? So I want to find how much interest is equal to my principal of 1,000 times my rate, which is 10% or 0.10, times my number of years, 5. So when we do this, we get $500. That's what we should end up getting. Stop. Okay, so let's see here. So it says, let me make sure. So it says, how much total interest will we receive in 5 years? So we'll receive $500 for 5 years, or $100 per year for 5 years. Okay. Now, now let's say that instead of doing simple interest, it says, what if the bond were paid? Let me make sure I'm on the right page here. Okay. So we could also think of it this year. In this situation. So once again, we get $500 for the full 5 years, or we could think about it as $100 per year for 1 year. Okay. So let me go down. Sorry, guys, my cat is actually jumping on my screen right now. Sorry about that. Okay, so I haven't given you the formula for compound interest. So it says, if the bond paid compound interest, how would you receive more or less, or would you receive more or less in total interest? Okay, so compound interest, we need a formula. We need a formula, right? Okay, so your book has a formula and it gives you this. It says accumulated balance after Y years, so A, so this is like the total amount of money. It's not how much interest, it's how much money is in this account, or if you want to say in this investment or in this loan, whatever the case may be. P, once again, is the starting principal, so we're okay with that. Then it says you multiply 1, you say the interest times 1 plus the annual percentage rate, okay, APR. Okay, so I wasn't taught this formula. I was taught this formula. I was taught A equals P times 1 plus R over N to the N times T, okay? So number of years, okay? So in your book, they call it Y, so I'll say um, N times Y for us. Now what N stands for, so N equals number of times the interest is compounded per year. So now here's the thing, is we're going to use this formula, and then I'm just going to show you why I just memorized this formula. This one is one that I prefer, just because I don't want to memorize a formula that only works sometimes. This one only works when it's compounded once per year, okay? But what if they compound it monthly? What if they compound it daily? What if they compound it half or quarterly? You know, we'd have to learn a new formula. This one always works. So this is the formula I recommend you use, but I'm just going to kind of show you how the book does it at first, and then we'll kind of, you know, move on to the way I want to show you. Okay. So over here it says compound interest. How much compound interest would we earn? Okay. So we're going to do our compound interest formula. Okay. So again, they're saying that it's going to be only compounded one time per year. So we're going to say that our actual dollar amount, okay, is worth the principal times 1 plus the APR, the annual percentage rate, and then times the number of years, okay? Technically, it's Y times N, but N is only 1 because it times the number of years. So we want to find out how much money we have in our account. Okay, the principal is 1,000, right? Times 1 plus, now the annual percentage rate is 10%, 0.10, times the number of years is 5. So what I'm going to do is I'm going to take out my calculator, and I'm going to do 1,000 times 1 plus 0.10, close parentheses, to the power of 5. And I hit enter, and I get $1,610.51. So I would get $1,610.51. Now notice, from this one, we acquired $500 in interest, but it didn't actually tell us how much money was in the account. So for simple interest, we would have to take, and we would do, well, we started off with $1,000 investment and we added 500. So we now have 1,500. So we can now see that for simple interest versus compound interest, right? So this is compound interest and this is simple interest. Okay, so compound interest gave us about $110 more, give or take, right? So, and again, sorry, this is money as well. Okay, so we definitely made more with compound interest. So here's basically what compound interest is saying. Okay, so in this next, let me see if it says it here. Yeah, so this is a good example. So I just want to kind of go through this. So it says, therefore, you receive a total of $500 in interest over 5 years. With compound interest, you receive more than $500 in interest because the interest each year is calculated on your growing balance rather than your original investment. Okay. So when they say the second interest payment, well, if you were using if you were using compound interest, you would take 10% of $1,100, but because remember, after 1 month you gained $100, so now your principal, or not your principal, but now your new dollar amount is 1,100. So when you take 10% of that, you get 110. So that means that you now have 110 on top of the 100, so you actually have $1,210. And then if you did it again, you would take 10% off of this, and then 10% off of the next, or off of 1,210. So the reason compound interest is kind of cool, I guess if you're investing, it's really bad if you're borrowing. Compound interest takes interest and you get a certain amount of money for it, and then you charge interest on top of the interest. So that's how it can get a little bit out of hand. Now, there is something in calculus that we talk about, a limit that it will reach, but we're not going to talk about it in this class. And we'll just kind of talk about continuous compound interest, which is basically our version of as bad as it could get in terms of borrowing, or as good as it could get in terms of investing. Okay. This raises your balance faster than simple interest. So compound interest, okay. So a good way to think about it is compound interest applies interest, compound interest. I should just erase it. Compound interest applies interest to the money you have borrowed or invested. So compound interest applies interest to the money you have borrowed and borrowed or invested in. Interest to the money you have borrowed or invested in. And the gain, I'm not saying this right. Compound interest applies interest to the money you have borrowed or invested in. However, it applies the interest to the new amount and not just the original principal. Right? So with simple interest, it's always just on the principal. Whatever the principal is, they apply the interest to that, boom, done. You find out how much it's going to be, whether it's a borrowing amount or whether it's an investing amount. However, with compound interest, it basically says that if you have $100 and then, if you have $100 and you get 10% interest on that, you would get $10, right? So you now have $110. And then if you take 10% interest on that, it's not $10 anymore. It's now $11. Okay. So now you have $121. And if you take 10% interest on that, you now have $12.10. So notice in simple interest, you would just have the $10, the next year $10, the next year $10. Okay. So 1 year would be $10. But with compound, interest, we just get to keep going. We get to, this year is 10, the next year is 11, the next year is, maybe I should do with dollars. The next year is $12.10, and then you got it. The next year, this would be what, 133.10. And then we would get times 10%. So we would get $13.31, right? So each year, instead of just getting $10, we're actually getting a little bit extra each year because we're applying interest on top of the previous amount, right? So we're adding our new interest onto the dollar amount that was the principal, and then we're doing it over and over again. So each time it's increasing by a little. And then simple interest would just do this. You have $100, you take 10% for the first year, you'd get $10. Next year, you have $100 still, you take 10%, you'd still get $10. You got another $100, you take 10%, the next year, you still get $10. Okay, and then so on and so on. And this one keeps getting a little bit bigger, and then this one just keeps saying 10, staying $10. So again, this is, we can think of this almost like as linear. It's the same amount each time. And then this one is kind of growing exponentially or in a different way than linear, if you don't want to think about it like that. Okay, so this raises your balance faster. So this formula right here, you guys kind of got to know. Now, this is, again, the formula the book uses, which is totally fine. But this is kind of the catch-all that works for all compound interest besides continuous compound interest, okay? So it says you invest $100 in 2 accounts that each pay an interest rate of 10% per year, but one pays simple interest and the other pays compound interest. Make a table to show the growth of each over a 5-year period. Use the compound interest formula to verify the results in the table in the compound interest case. So I kind of did that for us already. So as we see here, the first year we have 110, the next year we have 120, 130, 140, 150, because each year we gain $10, right? So that's what I was doing right here. I was showing you guys that each year we're going to gain $10, $10, $10. So if we have $100 in our account, next year we have 110. Then we gain another 10. The next year we have 120, then 130, then 140, then 150. And that's exactly what this table is trying to show you is first year, after you get your interest, you'll have $110. And then next year, you're still only getting $10 interest. You now have 120. You now have 130 each year, okay? However, this one, 110, 121, 133, so boom, boom, boom. That's what I was trying to show you over here with this. That's how I'm going to have an extra $10. So now I have 110. Then the next year I get 11. So now I'm going to have 121. Then the next year I have 121 and I gain 1210. So now I have 133.10. So that's what they're trying to show you with this table is the same amount of years, 110, 121, 133, and then here. So you're going to get $161.05, and here you're only going to have 150. So this makes you an extra $11.05. Now that may not sound like too much, but now think about that over, instead of investing $100, what if you invested $1 million, right? So that extra 11 is no longer just a little small lump of some money. It's a large amount of money. Okay. So that's kind of, that old expression, the rich get richer, is because if you have money to invest and you can acquire money off of your money, then, you don't necessarily have to even work. You could just live off the interest. There was an old thing when I was a kid that we used to always talk about, hey, if I won $100 million in the lottery, I could just live off the interest. I would never even have to spend that money. I could just live off the interest from the money, which is true. You would make a lot of money from that. Just from the interest, not even doing anything with it, just the money you make every month off of that. Okay. So it says to verify the final entry in the table with the compound interest formula. So let's do A equals, what I'll do it in blue. A equals principal of, was it $100 in the formula? Yeah, it's only $100. Sorry about that. Times 1 plus APR of 10% times number of years 5. Now I think I may have already done this. Oh, I think I did it with 1,000 though. Okay, so that's why the numbers sound familiar. So when I'm going to just type this in my calculator again, I'm going to do 100 parentheses 1 plus 0.10 close parentheses to the 5th power, and I get $161.05 on my calculator, and that's that number. So that's where they got that number from. It's not just made up. They're actually using this formula with compound interest. Now, again, the interest is only compounded once per year. Again, there's other ways they can do it daily, every minute, every second, every thought. They can compound interest however they decide, or however it's set up for that particular investment or loan. So now we show how quarterly compounding affects $1,000 investment at 8% per year. So let's do it 2 ways. So what I'd like to do is, we know our principal is 1,000 again. Okay. And now this time our APR, or let's just say our rate, is equal to 0.08. Remember, 8% is actually 0.08. Do not put 0.8, because then you're saying you have an 80% interest. Okay. And then the number of years, compounded quarterly. Quarterly. So that means 4 times per year, right? So that's where I would say that N equals 4, because it's compounded quarterly 4 times per year. Okay. So I'm going to take my formula. A equals, I'm going to take $1,000 and I'm going to compound it 1 plus, now I'm going to do 0.08 divided by 4. So this is the formula that I showed you guys over here. So this one takes into account our N. Okay, so we have to account for that. This one is only if it's compounded once per year, so that kind of makes it easy in a way. Okay, so they give you like this really easy formula. There is this formula which is a little bit more difficult, so that's what we're going to use. Okay, and this is just N times T. So N is 4, and T is the number of years, or in your book, Y. I think it's over 5 years again. Let's see. Oh, no, they just want it for 1 year. Okay, so we'll do it for 1 year right now. And then we can see how much would that do in 5 years or something like that. So we're going to do A equals 1,000 times, now we're going to do 0.01 plus 0.08 divided by 4. So I'll just write this out for you guys, 1.02 times 4. If you don't want to like do it as much in your calculator, I just added these two up first. Okay, so now this should become to the fourth power, 1,000 times 1.02 to the fourth power. And that should be $1,082.43. I rounded off a little bit to the nearest penny. Okay, so $1,082.43. And look right here, same exact thing. Now what we could do is, well, how much would this investment be worth at the end of 10 years? So let's do A equals 1,000 times 1 plus 0.08 divided by 4. And then we're going to do quarterly times 10 years. Okay, so let's see what we get. So I'm going to do 1,000 times 1.02 to the 40th. And I get $2208.04. So this would be $2,208.04. So that means we took $1,000 and turned it into $22, and it took 10 years to do it. Okay, so we gained about a little over double. That's sometimes they want to know the doubling rate or the half rate, how long, for radioactive decay, but we don't really do that in this class. But for doubling, they might ask you, okay, how long would it take, using the same stuff, would it take to triple your investment? Okay, so that means I started off with 1,000 and I want to end up with 3,000. So what I'm going to do is I'm going to do 3,000 equals 1,000, right? Because they want to know how long that's going to take. Oh, wait, sorry, you guys, we don't have, this is, I got a little ahead of myself. In order to solve that, we need logarithms, and I don't teach that in this class. Sorry about that, I forgot. But that would be my follow-up question if you were taking me for a pre-calc class or for a Math 110 class, is I would then ask you to find how many years it would take to double your money or triple your money. So we see that it's going to take 10 years to get a little above double. So then I would say it's probably going to take like 8 or 9 years to probably double my money, but that would just be an estimate because I don't have logarithms to go back and back solve for t. All right, so forget about this problem I did over here, guys. That one's for a different class. Sorry about that, I got carried away. So let's see here. Compound interest formula for interest paid in n times per year. So this is what I was talking about, the n right there. And in my formula, I just use a t for time instead of y for years, okay? But I think the y is totally fine. And I don't use APR, I just use R, or for the interest rate. But whatever you guys want to use, you should be okay with that, as long as you know how to use this formula, okay? So it says monthly compounding at 3%. So let's try another practice problem. It says you deposit $5,000 in a bank account that pays an APR of 3% and compounds interest monthly. How much money will you have after 5 years? Okay. So let's take a look here. So let's do after 5 years. So we're going to do the first part of this problem, and then we'll do it only once per year. So it says you deposit $5,000 in the bank. So our initial investment is $5,000. That's our principal. And then we do 1 plus 0.03, 0.03 divided by, now they said we're compounding it monthly. So there's 12 months in a year. So that's 12 times per year. Then we're going to do 12 times the number of years, which is 5, right? So let's see what we get. So I'm going to take out my calculator once again, and I'm going to do 5,000 times parentheses 1 plus 0.03 divided by 12, close parentheses, to the power of, what is that, 60? 12 times 5 is 60. So I get $5,808 and approximately 8 cents. Okay, so it says how much money would you have at the end of 5 years? If you compound it monthly, we would get $5,808. Now they ask you to compare that if you only did it compounded once per year. So we're going to do the same compound formula. We're going to do 5,000, and we're going to do 1 plus 0.03 divided by 1, and then we're going to do 5 times 1. right? Because it's only one time per year, n is equal to 1. So let's see what we get this time. So I'm going to do 5,000. Now you might think it would be way less, like way less, but that's something that's kind of tricky about compound interest. It has a limitation on how much it can keep compounding, how much it affects the dollar amount. So 0.03, 1 plus 0.03 divided by 1, I guess I didn't need that, to the power of 5. So I get $5,796.37. Now you would have thought like that would be a much different amount. So let's do 1.03 to the power of 5. Times 5,000. Now you may have thought that you were going to get a massive difference, but in reality, this is compounded 4 times per year, or I'm sorry, monthly. Sorry about that. Monthly. So 12 times per year. You would have thought that would be a lot more money. And this is only compounded once per year. So I would have thought, look at this power. This is a power of 60. This is a power of 5. But the way it works out is it was actually only about $8 difference, give or take. So really only about $8 difference. So somebody might say, hey, we're a really good bank. We're going to really help you guys out. We're going to compound your interest 12 times a month. And then you're going to be like, wow, that's really good. This other bank was only going to do it 1 time per month. 1 time per year. 12 times per year versus 1 times per year. I know I said it wrong, but you guys get it. But in reality, what the bank's really saying is that the difference is about, oh no, it's not 8, it's about $12. Sorry, my math is off. That looks about like $12. Okay, because 5808 minus 5796. Well, you know what? I'll just do it. 5808.08 minus 5796.37. So I get about 1171. So just about $12 difference, okay? And that's one's compounding at 12 times per year and one's compounding at once per year, okay? So for interest paid only once each year, we find the balance after 5 years by using the formula for compound interest paid once a year. So we already did this, okay? We just did that above. It says, after 5 years, monthly compounding gives you a balance of 5808 and 8 cents. Okay, while this one gives you 5796, so that's 1171. So that's what we just did. Okay, so this is just summarizing what we just did mathematically. Okay, though APR is the same in both cases. So yes, it is different, but I would have thought it would have been a lot more just because of the number of compounds that I was doing per year. It just felt like it should be more, but it turns out to not be. And that's kind of something that's misleading about compound interest. The annual percentage yield, also called the effective yield or simply the yield, is the actual percentage by which a balance increases in 1 year. It is equal to the APR if interest is compounded annually. It is greater than the APR if the interest is compounded more than once per year. Okay, so APR versus APY. So APR is annual percentage rate and APY is annual percentage yield. They are the same thing if it's only compounded once per year. But if interest is compounded more than once per year, like in the previous problem, then the APY would be more than the APR, okay? So the annual percentage yield, also called the effective yield or simply the yield, is the actual percentage by which the balance increases in 1 year, okay? So let's see here. Show the difference in compounding periods affecting APY for an APR of 8%. So if you compound once per year, right here, right? So they're saying n equals 1, and you have an 8% annual percentage yield. That means it increases annual percentage with the various numbers compounding per n. So they're using APY of 8%. And then for this one, they're using n equals 4, 12, 3. Now 365, what does that mean when you see n equals 365? That means they are compounding the interest 365 times a year. That means daily, okay? Then they can do it 500 times. Then they can do it 1,000, 10,000, 100,000. Well, no, that's a million. And then this is 10 million. And this is 1 billion. But what do you notice about these numbers? So it started off at 8%. And here we're at 1 billion times it has compounded the interest. And it's only increased by 3%. So that's that limit that I was talking to you about. Something happens when you start trying to compound interest a whole bunch of times. As the number of compounds increases, it doesn't actually effectively increase the yield as much as you would think. Okay, it doesn't increase the amount of money. Just like we see over here, you know, I would have thought if we were doing this problem that compounding it 12 times, $5,000 compounded 12 times per year versus $5,000 compounded only once, I would have thought the 12 times would have blown it away. We would have made a bunch of extra money, but we only made about 12 bucks, $11.71 extra. Okay. So, and again, I know if you're talking millions and millions of dollars, that does add up. But again, I would have thought it would have been more. So what this table is trying to show you is if you go through and do the compound interest formula for 8%, right? So you do the same thing that I was doing, but you just keep doing a different number of compounds. So you compound it once per year, then you compound it 4 times per year, 12, 365, 500, all the way to a million. It's really not going to increase the amount of money that you get as much as you would think. It's a very small amount. I mean, look at, if you do it daily, you're at 8.327. If you do it a billion times in a year, you're at 8.328. You're only off by what, a thousandth of a percentage point, right? You're off by a thousandth of a percentage point. That's the only increase you got, is about a thousandth of 1%. Okay, that's really not that much. Okay, so again, that's what this table just wants to kind of demonstrate to you, that if you do it enough times, we run into something called compound interest formula for continuous compounding. So imagine we could just keep going with this table, right? We could do, you know, 100 billion, or we could just keep going and just make a bunch of zeros, and it's still going to be around 8.328 and some change, right? Notice it didn't even change much. 8.328706, 8.328706. It didn't even change for 6 decimal places. Okay, so this new formula comes from continuous compound interest, saying that we're going to compound it so many times you can't even think about it. Every thought of a half of a second of a split of as much as you can think, that's how often we're compounding it. And this is a much easier formula to work with. It uses the natural number E. So the way I was taught was A equals, and I was taught PERT, P principal E R to the T. I'm sorry, P E to the RT. So we have the rate times the time. They call it APR times the years. I call it R times T, number of years. Okay, so whichever way you want to do it, that's fine. But this one I just memorized really easy because it sounds like PERT, like an old shampoo when I was a kid. So we just memorized it pretty well. Okay, so once again, E is a special irrational number with the value of E is approximately 2.71 and some change. So that's called the natural number, and that's the value it carries. Kind of like pi, how pi is about 3.14 and some change. That's not exactly what it's worth, but that's about what it's worth. And E is a naturally occurring number like that as well. Okay, it's an irrational number. So let's try continuous compound interest. So you deposit $100 in an account with an APR of 8% and continuously compounding. How much will you have after 10 years? So look how easy this formula is. A equals P E R T. So I'm just going to say A equals $100 times E times 0.08 times 10 years. Okay, so on my calculator, I'm just going to do 100 times second function E, there's E right there, to the power, and then you may need to use parentheses. I don't need them because my calculator already has it, but you guys may need to use parentheses. So I'm going to say parentheses 0.08 times, I think it was 10 years, right? Hopefully it was 10 years. Yes. So they get $222.55 if we round off. So we get $222.55 if we round off, okay? So that's if you've compounded it. This is continuous compound interest. This is if you compound it every thought that you have of compounding, every split moment in time, that's how many times you're compounding. And it's even more than that. It's approaching an infinite amount of compounds. And you get about $222.55. Let's do the same thing, but let's say we compound it, you know, quarterly, okay, 4 times a year instead of a near infinite amount of times. So I'm going to do A, let's do continuous, or not continuous, I'm sorry, regular compound interest, not continuous, okay. Regular would be A equals, and now I'm going to do $100 times 1 plus 0.08 divided by 4, because we're going to do quarterly. So this would be quarterly. And then we're going to take it to the power of n, which is 4, times t, which is 10 years. So now let me take out my calculator. I'll do it on my handheld calculator just to be faster. 100 times 1 plus 0.08 divided by 4 to the power of 40. And I get $220.80. So notice we only gained, what did we gain? $2? Not even $2, like $1.70 by compounding it in near infinite amount of times versus compounding it quarterly. This is near infinite amount of compounds. We are approaching an infinite amount of compounds. We only gained $1.70. So that's what they're trying to show you, is that sometimes it's just easier to use continuous compound interest, and the difference isn't worth the trouble. Obviously, you know, in banking and everything has to be exact, and pennies missing or pennies missing. But this to me is the easiest formula to work with, especially the easiest one to memorize. This is a little bit harder formula to memorize. So it's a little bit of sometimes more trouble than it's worth. But again, the way you know to use continuous compound interest is they will say compounded continuously, or they will say compounded monthly, quarterly, weekly, daily, every minute, every second of every day. You know, they can just keep talking about different amounts of compounding, and you have your formulas to do it. Okay, you guys, so that's pretty much it. That should get you through most of the homework for chapter, what is it, 4B, I believe? Yes, 4A I left for the homework to show you because it's a very straightforward section. It's not really anything, it's just stuff that, you know, you just read a few, watch a few of the videos that are provided in the My Math Lab, and you should be okay. I'm going to focus more on 4B and 4C, but please do the homework for 4A. It's not too bad. All right, you guys, that's going to do it for this video. Thanks for watching.